Hi everybody, it is now the 8th of December, and I want to kind of pick up where I left off yesterday, so I'm working through Advent of Code, writing code for the GPU. I skipped over the weekend, so yesterday I caught up doing like the 2 days from the weekend, and then tried to do yesterday's problem as well. Yesterday's problem was like a graph problem, which I couldn't find like a decent GPU solution and kind of gave up after doing it for a little while. So what I want to do today is revisit yesterday's solution a little bit, just to see if I can kind of get to the end of it, and then move on to day 8. So let's just have a look at where I got to yesterday. If you want to kind of catch up on this, go and check out my YouTube video where I've like already gone through like what we're doing in this problem. But where I started using NetworkX, which is a Python library for dealing with graphs, and then I've also imported cuGraph here, which is a GPU accelerated implementation of a graph library, and it has like API compatibility with NetworkX. So first thing I did is create myself an empty graph, go through the problem, and construct a graph from that. Right. So I've put together this graph object, and if we have a look at like the graph nodes, we can see all the different colored bags. Right, this was all about putting bags inside bags inside bags, and we can see all that, the edges and stuff here. So constructing this into an object was pretty nice, and then part 1 was a case of doing a breadth first search to work out kind of all of the nodes required to get all of the routes that you can get to shiny gold from, and then just calculating the set of those. So it came out with 148, and I got the right answer. So part 2 of this was all about now working out how many bags you need to do. So this isn't a GPU solution, this is a CPU solution. I tried yesterday to kind of swap out for cuGraph, but I think this is such a small graph and it's such a small problem really, that the GPU code is just not in a place to run this. So this is like a CPU solution. I'm probably going to come and maybe do a CPU solution for the second half as well. I'm going to limit myself to doing this for like 15 minutes, and if I don't get to the end of this in 15 minutes, then I'll stop and we'll move on to part 8, to day 8. So I'm going to read this through again, just so we can kind of get back to where we were, and then we'll try and move forward. So it's getting pretty expensive to fly these days, not because of ticket prices, but because of the ridiculous number of bags you need to buy. Consider again your shiny gold bag and the rules from above. So we had these rules where, this bag contains a certain number of, they each contain different bags, right? So faded blue bag contains none, the dotted bag contains none, vibrant plum contains 11, dark olive contains 7, and then, those have to contain different things. So a single shiny gold bag must contain 1 dark olive and the 7 bags within that, plus 2 vibrant plum bags, and the 11 bags within each of those. We end up with we're kind of traversing the graph here, right? So we're starting at shiny gold, and we're kind of walking through all the bags that are inside it and multiplying. We're effectively multiplying the weights of the edges together. So of course the actual rules have a small chance of going several levels deeper than this example. Be sure to count all of the bags, even if the nesting becomes topologically impractical. That was a mouthful. Here's another example. In this example, a single shiny gold bag must contain 126 other bags, right? Because shiny gold bag contains 2 dark red contains 2 dark oranges contain 2 dark yellows, etc., etc., right? So there's a lot of recursion, a lot of nesting going on here. So what we almost need to do is walk through each type of bag and work out how many bags need to go inside it, and then work backwards, kind of multiplying all of those answers together. So let's just have a look at my graph. Let's just actually, let's give me a part 2. So this graph, this should be a code cell. Code. Right, so we have our diagraph here. What I want to do, let's carry on with NetworkX. NetworkX Python And then I want to have a look at the reference. What I want to do is go into each, I want to like walk through the graph, right? So is there utilities do we have? I mean, I guess methods. What I want to do is have a look. Neighbors returns an iterator of successor nodes in n of n. Okay. So let's have a look at that. Let's just, I'm curious. I might actually play around with the sample as well. Let's move this into a function. And then I can kind of play around. So let's do def read data. And we'll give it a file name like that. Be file name. I'll put that in there. And then we'll return the graph. Return graph. And then here I'm going to do graph equals read data of our file name. That should still give us the same graph with the same thing here. But I'm just going to, just for this example, let's do like a sample graph, and we'll have a new file called sample. I've already got a sample, but I'm going to copy this one, right? Because it's given us, here's an example with 126 other bags. So let's replace my sample with that. So then if I have a sample graph, it now looks like that from my sample input. So reading that in, we should have an answer of 126 bags. So we want to walk through that. Let's just have a play around with the graph object. So we have sample graph, and we want to do neighbors of n. I think if I do neighbors and give it, was it shiny gold? Shiny gold. Oh, and it's giving us an iterator. So if I do list on that, not length, list on a shiny gold bag, there's nothing. Okay. I think because the graph's gone the other way, so maybe this is successors, or is it predecessors? Predecessors. Dark red. Okay, I think that's right. Yeah, shiny gold bags contain 2 dark red bags. So here's our dark red bags, and we should have a weight as well. Let's see, how can we get that? Get edge data, maybe? If I do sample graph dot get edge data of shiny gold and dark red. We've got shiny gold and dark red. That didn't do anything. Has edge is a boolean. Get edge data returns the attribute dictionary associated with the edge UV. Or maybe it's the other way around. Yes, so we've got a weight of 2. So we're going to want some kind of recursion here to walk through this, but I'm going to need to do like for bag in sample graph predecessors shiny gold sample graph dot get edge data, and this will be bag and shiny gold still, and then let's call this weight. Let's just print that, print out the weight. Okay, so 2. And then we're going to need to multiply our answer in here somehow, aren't we? So then we need to like iterate through this somehow. So there's def count bags. And let's call this bag like that. And then we need to return this thing here, right? They've got this bit of math here that's like 1 plus 1 times 7 plus 2 plus 2 times 11. So we need to like build up that bit of maths basically. So for bag in sample graph predecessors bag, and that will also be bag. Oh, and this will be let's call this like nested bag, like that, and then we'll do count bags on shiny gold. Okay, so we're printing this out, but what we actually need to do here is we want to actually call count bags on the nested bag. So we end up doing that. Okay, so now we've got lots of 2s. Let's count. Let's print our nested bag as well, just so you can see what's going on. Print nested bag. Maybe I'll put this after so it goes that way round. Yep. So we've got dark red to dark orange to dark yellow to dark green, dark blue, dark violet, etc. Right. So we've got this here. What I'm worried about is we're going to hit like a depth error of recursing too far on our actual input. But let's see how we go. So what we need to do actually is, instead of printing things, we need to return the number of bags. So it will be the weight times by count sample bags or something. And this would be like count equals that. I'm gonna go count equals 0. Count plus equals that weight, and then we need to return count. Count equals 0 for bag in nested bags. Count that. No, it needs to be count equals 1. 127. That's not the 126. I think right. I think count does need to equal 0, but then for bag and nested bags, it needs to be the weight times count bags plus the weight, isn't it? Yeah, so let's go weight equals that, and then it will be weight plus weight times count bags. 126. Okay, good. That's given us the answer that we wanted here. So now let's just try doing this on our regular. Oh, we want to pass it a bag and a graph. This graph here, let's get rid of that, and then this will be our sample. Ooh, I keep doing that. I keep changing my cell type. Sample graph. Sample graph. Missing one. Oh yeah. 126. Okay. So now let's try doing count bags on graph and see if we hit a recursion error. No. Okay. Answer. Submit. That's the right answer. Okay. Lovely. That was fine. So we've got a CPU solution using NetworkX, which is fine. Now let's. I'm just going to delete those here because we don't really care about any of that. I'm just going to restart and make sure I can run through from the beginning. So let's import these things, read in our input data. We can have a look at the graph if we want to, but I'm going to just shrink those down. In part 1 we should get 148, which we do, and then part 2 we're going to get 2876. Okay, that's fine. That worked. So we have a CPU solution but not a GPU solution, and I don't think it, like, I couldn't find this BFS predecessors in cuGraph, but I think that's like the point of cuGraph, right? Is that it's implementing these methods. It's just that maybe at the moment is only tackling some of the larger scale problems here. And then here we're literally walking our graph like with recursion in Python GPU is just not kind of set up for doing this kind of thing with recursion like this. So it is what it is. That's kind of the end of that. So that's it. We've done it. I've got my stars, which I'm happy about. So let's move on. Let's move on to day 8. So day 8. Let me read this out. So your flight to the major airline hub reaches cruising altitude without incident. While you consider checking the in-flight menu for one of those drinks that come with a little umbrella, you're interrupted by the kids sitting next to you. Their handheld games console won't turn on. They ask if you can take a look. You narrow the problem down to a strange infinite loop in the boot code, which is your puzzle input of the device. You should be able to fix it, but first you need to be able to run the code in isolation. The boot code is represented as a text file with one instruction per line of text. Each instruction contains an operation and an argument. Okay. ACC increases or decreases a single global value called accumulator by the value given in the argument. For example, accumulator plus 7 would increase the accumulator by 7. The accumulator starts at 0. After an accumulator instruction, the instruction immediately below it is executed next. JMP jumps to a new instruction relative to itself. The next instruction to execute is found using the argument as an offset from the JMP instruction. For example, JMP plus 2 would skip the next instruction. JMP plus 1 would continue to the next instruction immediately below it. And JMP minus 20 would cause the instruction 20 lines above to be executed next. NOP stands for no operation. It does nothing. This instruction immediately below it would be executed next. For example, consider the following program. Right. These instructions are visited in this order. First, the NOP plus 0 does nothing. Then the accumulator is increased from 0 to 1. Then JMP plus 4 sets the next instruction to the other ACC plus 1 near the bottom after it increases the accumulator from 1 to 2. Okay. JMP minus 4 executes, sets the next instruction to the only ACC plus 3. It's the accumulator to 5. Then JMP minus 3 causes the program. Okay, that's fine. This is an infinite loop with the sequence of jumps. The program will run forever. The moment the program tries to run any instructions a second time, you know it will never terminate. Immediately before the program will run an instruction a second time, the value in the accumulator is 5. Run your copy of the boot code immediately before any instruction is executed a second time. What is the value of the accumulator? Okay, so this is, we have to write like this is like an emulator, like a virtual machine kind of thing. We have like a series of instructions. I can't imagine, like these are sequential instructions written for a CPU, so I can't imagine that we could do this with a GPU and get any benefit from it necessarily, I guess. The only thing I can think is maybe you could map over all the instructions and say like what is the next instruction and then see where there's a collision, but you would need to know all the outputs of those. Yeah, I think I'm just gonna have to write some like Python to step through this. I don't know if I can do this on the GPU, but let's do it anyway. Let's make a new folder, call it 08. Have a new file, call it solution. Oh yeah, I started renaming them differently, didn't I? I call this 08 solution. And let's call this day 8. What did I call it in here? Data processing. Data processing. Let's try and be consistent. I've been really consistent with these titles, but inconsistent. Let's have a new file. Let's rename this one and call it input. This will be our like main input. I'm also gonna have a sample. I've been skipping doing the samples, but I'm gonna have the sample just because it's a good sanity check to have. We've got our example here. Sample text here. Fine. Yeah, okay. And then let's get our actual puzzle input as well. Input like that. Fine. So our data processing, the first thing we need to do is read this in. So let's have let's define ourselves a read data function with a file name like this, and then we'll say with open file name as a file, and then we'll do for row in fh dot read lines, and then we'll do row equals row dot strip. Okay, so the next thing I need to do, let's have a look at the sample. We have our operations. We just have 3, don't we? Let's split it on the space. We'll have our operation and our counter equals row dot split with a space, row dot split on a space. And then for our counter, we need to do like an integer from a signed string. So let's go Python integer from signed string. Okay. Oh, can you just do that? I've never done this before. If I just do int of -1, we get -1. If we do int of +1, we get +1. Okay, that's very easy. And let's just say counter equals int counter. Oh, we could probably actually do this in a list comprehension, couldn't we? Let's unpack this a bit. So we'll do no, let's not. Let's go like this, and we'll have our out our data is a list, and as we iterate through, we will do data.append operation and counter as a tuple. Okay, and then let's do read data on our sample. Oh, we need to return data. Return data. Okay, that's fine. We've got our set of instructions like that. And then let's do part 1. What we're going to need is we're going to need to step through, right? So we need to write the logic of stepping through this program. So we're going to just like need an index and an accumulator. And then we're also going to need like a list of executed instructions. So let's say executed equals a list. We'll have our accumulator is going to start at 0, and we'll have our pointer is going to start at 0. And then we'll say while pointer not in executed, and then we need to step through and do our logic. So we need to do let's just do some if statements in here. There's ACC. If we have ACC, if oh yeah, let's go data equals that, and just data, right? If data I might actually unpack these again. So we'll have operation counter equals data at pointer, and then executed dot append pointer, and then I might make that the first thing. Oh no, we'll unpack that and we'll add that there, right? So we're doing this step. And then we'll say if operation is ACC, then it'll be plus equal, we'll have accumulator plus equals counter. Jumps relative to itself, right? So if operation equals jump, or mixing quotes, which I shouldn't do. then oh, and pointer plus equals 1. Jump is pointer will be plus equals counter, and then the last one was nop, which is nothing. So we'll do if operation equals nop, then pointer just plus equals 1. And then at the end, we want to print, we want to, what's our accumulator? 5. And that was the answer here, right? The answer is 5. Good. So let's try doing that, but now on our actual data. So we won't do this on sample, we'll do this on input, like that. Let's just truncate that so we can see a bit, right? Then if we run this again, the answer is 1675. Submit. That's the right answer. 1 gold star. Continue to part 2. Okay. Part 2. After some careful analysis, you believe that exactly one instruction is corrupted. Somewhere in the program, either a jump is supposed to be a nop or a nop is supposed to be a jump. No ACK instructions were harmed in the corruption of this boot code. Okay. The program was supposed to terminate by attempting to execute an instruction immediately after the last instruction of the file. By changing exactly one jump or nop, you can repair the boot code and make it terminate correctly. For example, consider the same program from above. If you change the first instruction from nop plus 0 to jump plus 0, it would create a single instruction infinite loop, never leaving that instruction. If you change almost any of the jump instructions, the program will still eventually find another jump instruction and loop forever. If you change the second to last instruction from jump -4 to nop -4, the program terminates. The instructions are visited in this order. After the last instruction, ACK plus 6, the program terminates by attempting to run the last instruction. Run the instruction below the last instruction in the file. With this change, after the program terminates, the accumulator contains a value of 8. Fix the program so that it terminates normally by changing exactly one jump to nop, or nop to jump. What is the value of this? So what we could do, I'm tempted here actually, we could like brute force this with a GPU. So the way we could handle this is we could count all of our nops and jumps and then map over that, like, and that will create our input of these are all the ones that could be flipped, and then we could change this logic so that we go through all the potential things that could be flipped, and flip it, and then run through this logic sequentially, exactly the same as we've done here. We need to change the data structure a little bit, but we do exactly the same things here as we've done here, and then just change a bit of logic here so that if pointer gets longer than the data, we return the accumulator, right? And that's the thing. Otherwise we return 0, and then we can call a max on our output array or something. Yeah, let's try it. Let's see what happens. We're effectively going to use the GPU to brute force this problem, which is actually quite fun. I'm gonna copy this here. Actually, let's make a new section. I'm gonna call it read data for GPU. We'll do this slightly differently. So let's copy our read data into a file called GPU. Now what we want to do here is, these numbers are fine, but these are not. We want an array, basically. We want this to be like a NumPy array that we can move to the GPU. So these instructions need to be like an ORD, basically, I guess, of those instructions, like, or some representation of these instructions that we can have as an integer rather than as a string. So we'll do something like instruction key equals it was ACK jump and nop, wasn't it? So let's do ACK is 0, jump is 1, and nop is 2. And then in here, operation is going to be equal to instruction key of operation. Okay, so this will now be an integer, and then we're going to append that. But let's also import numpy as np, and we'll from number import CUDA. This will be a numpy array, so we'll do np.as array, and let's put a list in here, and then data will be a numpy array as well. And then let's read our sampling again. So let's have let's do read data GPU of our sample. We get a numpy array that looks like this, right? So we have our instructions and we have our things. So that's fine. That's our GPU data. And what we want to do is we want to write a CUDA function. So let's just come and copy some of the input of one of my functions from here. This will be brute force flips, right? We're flipping bits, kind of, aren't we, basically? So we're going to take in our data. This will be our instructions, and we will take in, that's fine, we'll take in our instructions, and we'll take in an output array. So this output array, and then we need a new array, which is going to be, because this, yeah, we have our instructions, but we also need our bits to flip. Bits to flip, right? And what we want is every index that is either of the ones we're swapping. So jump to nop or nop to jump. So jump to nop. So 1 or a 2. Any of these that are a 1 or a 2, we need to read in. So we need to get, we can do this in so numpy get index where yeah, this would be like an np.where. So np.where let's call this instructions. This would be np.where any instructions is greater than 0. Instructions 0 slice, is that how I do it? No. Slice 0. Okay, so that's 2 0 1 0. Yeah, that's fine. That's not what I want to do. Okay, so we've got 0, 2, 4, and 7. Okay, that's perfect. That's exactly what I want. So this will be our bits to flip. Is this? Do I need to go like that? No, maybe not. So here we have an array of the indexes that need flipping. So this is what we're gonna map over on our GPU, is this bits to flip, and each thread on our GPU is going to flip one of them and then run through the instructions to see if we get to the end. So let's take that out. So position equals good one. If position is longer than bits to flip, then we'll short circuit. And let's oh, we need an output array as well, and that will be just np.zeros with the length of bits to flip. we probably want to put that in this. I tend to put that in here, right, and then have a look at it. And then we do output position. Just set it to 1 just so I can sanity check my output. That's not what I wanted to do. Yeah, see, this is not a thing, is it? Because length of bits to flip is 1. I'm sure if I do I need to unpack that into a list? Yeah, that's it. Now the length of that is 4. Now if I do that, we get 4 zeros. Oh yeah, okay, we've not actually called it. That's fine. I need to do my threads per block and blocks per grid logic here. Oh yeah, I'm getting a bit ahead of myself. Let's do that. So this is bits to flip. Like that. So we've got our blocks per grid and everything. And then we need to call that function. This is brute force flips, and it takes bits to flip instructions and output. Flip instructions and output, and we want to put our output. We want to create our output before there, and we want to have a look at our output afterwards. Just clean that cell up a bit. Instructions is not defined. Have I just mistyped instructions? What did I? Oh yeah, I just missed an S in instructions. Okay, so we got an array of 1s, and we launched that successfully on the GPU. So that's good. The next thing I need to do then is take this bit of logic here, basically. So we need our logic here, and we want our flip equals yeah, let's do this. Bits to flip. Our flip is bits to flip position. So this will now be the index of instructions that we want to modify. Now this is going to be a pointer, so if we modify it, we're going to modify it everywhere. So we probably just want to take the flip into account. We'll worry about that in a minute, instead of actually changing it. The next thing we need to do is we need our executed, our accumulator, and our pointer. Like that. Now executed is going to be a new array that is the length of instructions. No, that's not what I want to do. I want let's just try doing that. I know the length of this because this is going to be an array that's not longer than this. I just don't know whether we need to define that somewhere. While pointer, and then we want to do while pointer is not in executed. Do exactly the same things. Operation counter equals that. Append that to there. And then if operation, okay, so ACC is now 0 and JMP is now 1 and NOP is now 2. Okay, so this is going to step through, but we still need to flip our operation equals data pointer. So we'll do that, but then if let's put this logic in here. So let's flip our bit here. Flip bit. So if pointer is flip, so if it on this one that needs flipping, if operation is 1, operation is 2, and if it's 2 it will be 1. Operation is 2, it will be 1. Is that right? Yeah, because it's NOPs and things that we're doing. So here we are, we're going to flip that bit, and then we're going to get all the way through here, and then we're also going to say if pointer is greater than the length of our instructions, then our output at position is going to be equal to our accumulator. And we're going to break as well, right? Break out of our loop. Let's try that and see if it compiles. Typing error. Executed.append pointer. Unknown attribute append of type list. Yeah, that's what I was thinking actually, is I can't append to a list. So let's we're going to need our executed pointer as well. Let's make that equal to 0. And then executed is going to be a new array of the length of instructions. I think that will work, right? If let's just try a long trace, isn't it? Right? Yeah. If I do that, it will give me a list of zeros, and then executed pointer equals pointer, and executed pointer plus equals 1. Still typing error. Why does it not like that? Multiply a list. Okay, I can't multiply a list. Let's see, let's do Python create list with length. Yeah, see, this is what I would normally do. Oh yeah, maybe I could do it with range. Executed equals list of range of length instructions. No, still a typing error. List cannot determine number type of class type. I mean, I could create like an array to keep track of, right? But let's just have a quick Google. Let's go number CUDA append to list. Or go in functions list. Number for CUDA GPUs, supported Python features, built-in types, built-in functions, range. Or can I just do range, length of list like that? No. No implementation of function, set item found for signature, set item range state int 64. Mutable sequence types. I'm just in Python. Int float enumerate complex. Due to CUDA program model, dynamic memory allocation inside a kernel is inefficient, often not needed. This allows this. Okay, so I actually need to make this ahead of time. So I need to pass this in basically. This pointer as an array probably. Let's just try doing that. Let's just do executed pointer array equals mp.zeros, and it will be the length of instructions, and it'll be length of bits to flip by length of instructions. Okay, and then We're going to take in our executed pointer array. Pointer array. And then we're going to use that here. So because we need to count this. So our executed pointer array, we don't need executed at all here. And here executed at position and executed pointer equals pointer, and then while pointer not in executed, we need to slice this, don't we? So we're going to slice at position all of them. Right, let's try that. Still a typing error. What have I missed? No implementation of function. Get item found for signature. Let's say exec. Oh yeah, executed into array. Nope. No implementation for this. Contains array. I need to do like a. Maybe I need to do like np.any. I need to know whether any of this. Let's have executed equals here, this, right? This is our list of executed bits, which is just a list of zeros at the moment. While pointer not in our list of zeros. But we could do, if we can do numpy value not in array is in. Yeah, what if I can do np.is in element test elements? Test elements is that. Can I do while not np.is in, and then it's executed and pointer. Unsupported numpy function is in. Okay. That's fine. I wonder if I need to do something like let's just Google it. Number CUDA value in array. Because I need to make sure that we've not come back to this pointer, right? In an infinite loop. So it makes sense. We have our executed array, and we're like putting values in. So we're saying we've done this instruction and then this instruction and then this instruction and then this instruction, and we need to check whether like any of those values are in there. I mean, in a bug, there's a slight bug here because these are all going to be zeros. I wonder if, and obviously it's going to be 0 because this instruction 0 exists. But oh, these are the little problems that seem to trip me up. I'm like happy with what I'm trying to do in terms of I've got my flipped bit, I've got my accumulator and my pointer, and then I want to say while we haven't run this instruction, I wonder whether, I mean, okay, so the other thing I can think of is, what if we say keep going until you've gone through all of the instructions, or like you would have gone through all of the instructions, and so if we get stuck in an infinite loop, we're just going to keep infinitely looping for a while. That might be a thing. So while pointer is less than the length of instructions, and I'm just going to get rid of that, and I'm going to get rid of this, and I'm going to get rid of that, and this, and that. Still got a typing error. What's it not happy with now? Cannot unify Unicode type and literal integer. Why is there a Unicode type there? This is, something's wrong, isn't it? Let's just I'm gonna just start like this. So we've got our instructions. Let's have a look at our instructions. D type is in 64, right? We've got our bits to flip here, and then we're going to go through and do this. And we've got a typing error of name data is not defined. Where have I called data? Data pointer. But that's instructions, not data. That's why. Ooh. Okay. I've done something. I've done something. It made my GPU very, very busy. Wait. I know what I've done. I am infinitely looping, which is fun. Okay, I made my GPU infinitely loop. We did a thing. We don't want pointer, we also want counter is equal to 0. And counter is, well, counter is, no, it's not going to be called counter, is it? Let's just call this count. I don't know if that's a good idea. We got counter and count, but we'll have count. Let's call it call count. Call count plus equals 1. Okay, and then while call count is less than the length of the instructions. So let's restart. I'm gonna have to run through from here again. Read our data in. We've got our instructions. Don't actually need to look at that anymore. We've got our bits to flip, and then we're gonna brute force through, but actually calling the right things. Oh, that's a shame that didn't work. If pointer is greater than the length of instructions, maybe it's greater than equal to. No. Is less than or equal to length of instructions? Nope. Okay, let's walk through this example and see what's going on. So you change the first instruction from not to jump, it would create a single instruction infinite loop, never leaving that instruction, right? So we're that was exciting. Sorry about that. Punch my microphone. You change the second to last instruction from jump -4 to nop -4, the program terminates. The instructions are visited in this order: 1, 2, 3, 4, 5, 6, and then the pointer should be set to 7, right? Like, if pointer is equal to the length of instructions, I think that's right, isn't it? If pointer is equal to the length of instructions, then output position equals the accumulator. But we're not running through here. I'm still enjoying the fact that I managed to get my GPU in an infinite loop and make it very, very busy. And show, you know, my GPU utilization showed 100% for a long period of time. I'm tempted to just try this outside of here just to see if I can debug it like this. So let's say length of instructions, pointer, let's just say print accumulator, and then flip. Let's say flip equals 0, and we'll just run that, and it will just run, right? And it won't print. Well, let's just call this out and call it 0. And then here we'll say out equals our accumulator. And then let's just have a look at out. So out is 0 here. So the bit that we need to flip is the second to last. So 0, 1, 2, 3, 4, 5, 6, 7. 7 is going to get flipped. It's still coming up as 0. So why is that happening? Well, call count is less than or equal to the number of instructions. Call count plus equals 1. Then we're going to get our operation in our counter, and then we're going to flip our bits. So let's just print flipping our pointer. So we're flipping 7. We are at 7. If so, the operation is 1. So and let's put this in here. So we say now it's now a jump, and this is now a nop. Now a nop. Oh, it's flipping it back. I think it's giving us an answer. Okay, if I just change that to an elif, hey, it's given us the number 8 in there. So now we can do max of that because it will just be a number that's not 0, I reckon. Okay, so that's given us an answer. It's given us 8. And is that the answer? 8, the value is 8. Yes, good. Okay, now let's take the actual input and run this again. So we'll say input.text, like that. We've got lots more bits to flip here, so we're going to brute force it again, but it should still be fast. And we get this answer of 1532. Answer, submit. That's the right answer. Success. Excellent. Amazing. So we're 8 for 8 now on our advent calendar. So that was nice, right? So part 1 was a pure Python solution, which kind of made sense. But then part 2, we basically just wanted to brute force doing this lots of times. So it made sense to switch over to running it on the GPU and brute forcing. But the logic it was the same, right? It was the same as we did on the CPU once. But now we're like, flipping our bit and then running through many times on the GPU to try and figure out which one it was, and then we can kind of work out which value is the one that returned. So that's a reasonably nice example, actually, of doing something pure Python and then switching up to the GPU when you want to do the same thing but in parallel, which is what we did. So I will get these solutions committed. I'll push it up to GitHub. I'll get this up on YouTube. Thank you for watching. I hope this was useful, and I will see you next time.